All right, so the first algorithm we're going to cover based on evolutionary computing, you may or may not have heard it. It's what's known as genetic algorithms, okay? So genetic algorithms was pioneered by a scientist by the name of John Henry Holland from the University of Michigan, Ann Arbor specifically. And it's based on the ideas of the controversial topic of Darwinian evolution, so it's basically the survival of the fittest. So the ideas behind genetic algorithms is that it is a search technique that is used for computing true and approximate solutions to optimization and search problems. Okay, so it's inspired by evolutionary biology. So you would model your parameters based on chromosomes, and then you'd mutate these chromosomes in order to find the best parameters, and you'd use concepts such as inheritance, mutation, selection, crossover, and so on. So we're modeling this as finding a sequence of genes where each gene will be a parameter, and you'll hopefully find a chromosome that will best match or best optimize the cost function as best as possible. So here's some vocabulary before we start. Okay, so you could think of a cell in the human body as the basic, it's the basic building blocks of life. It's the smallest thing that can be used to replicate itself. And you can think of each cell contains chromosomes. Right, so a cell is the basic building block for basic building block of life, I guess you can think of it like that. Oh yeah, before I continue, sorry, I forgot to mention one thing. If you go back to the SOM example, I forgot to mention this. I forgot to multiply by 2 because the Gaussian is e to the power of that and divided by 2 sigma squared. I forgot to multiply by 2, but when you do the multiplication by 2, it works out to the numbers I have, because I have the multiplication of 2 in my notes, but I just forgot to write it down. But the numbers do actually equal out. So just make sure you put a multiplication of 2 underneath the Gaussian. Anyway, so a cell is the basic building block of life, okay? So each cell contains chromosomes. So you can think of a chromosome as having strands of DNA, right? Okay, and then each chromosome, so each cell contains chromosomes, and each chromosome contains a set of genes. Okay, so you can think of these as blocks of DNA. So you have the chromosome, which is a large container, then inside the chromosome you have a bunch of genes, right? So you have chromosomes and then the discrete unit is genes inside. So each gene determines some aspect of an organism. So one particular gene might define the color of your eyes, or one particular gene might define the color of your hair. So each of these genes defines some unique characteristic about you that makes you unique, all right? So each gene determines some aspect of an organism. So of an organism. I'm not going to test you on biological terms. That's not the purpose of this course. But I just want to give you an idea of where these terms come from when I actually lay out the actual algorithm in the end. So, for example, eye color is it could be defined by a gene in your system. Okay. So when you're talking about reproduction, when you're let's say when you have two parents that produce a child, you have genes that are combined from the mother and father to produce them and mutate them in some way that will produce a child that is hopefully the best of both of you combined into one person. Okay, so reproduction involves recombinations from parent genes and small amounts of mutations in copying. Okay, so this is an example of crossover where you take some portions from the mother's genes and some portions from the father's genes, so you have the crossover, and then you introduce some mutations along the way to make you unique. So those two combinations together makes person. Okay, so the fitness, there's another term, the fitness of an organism is how much it can reproduce before it dies. Reproduce before it dies. And obviously you want to have as many organisms that have a high fitness as possible. In our case, for optimization, we define the fitness of how likely these genes or these chromosomes will optimize your cost function. That's what we're going to use it in that context. So in our case, the fitness tells you how well the parameters lower the cost function. Okay. All right. So the fitness depends on the application. Like there's no universal standard for the fitness. It totally depends on the application. So for example, if you were using genetic algorithms to train, let's say, a logistic regression classifier, the fitness may be classification accuracy. So the higher the fitness, the higher the classification accuracy you want. In regression, people tend to use the negative of the cost function because the larger the cost function is, the lower the fit should be. So if you apply the negative, it gives you the opposite logic. So the larger the negative number is, the less likely that particular set of parameters will match. So some people like to use the negative of the cost function for regression, and people like to use classification accuracy for the function when you're taking a look at fitness. Okay, so the fitness function depends on the application. So for classification, you might want to use the classification accuracy. The higher the accuracy, the higher the fitness, right? So classification accuracy. Some people like to use that. There's no universal standard. It just depends on the application. And in regression, some people like to use the negative of the cost function. Right, so larger values of j mean that those parameters are unsuitable. So you want to make that the negative, which means that large negative numbers mean that it's unsuitable. All right? Okay, so you've got that. Okay, so let's see here. What's the final goal? Our goal is to find the right parameters of our, if it's the prediction model or prediction model. If you're doing supervised learning in that case, of our prediction model, regression or classification, it depends on what you want to do. That minimizes the cost function. Or in this case, that produces the largest fitness possible. Okay, so for example, the parameters might be theta for linear or logistic regression, or SVMs, right? That might be what the parameters are. Or if you're looking at neural networks, it might be the actual neural network weights, the neural network weights. It just depends on what parameters you're looking at. But either way, there's some parameters that we want to used in order to figure out, to have the best model possible for predictions and all that. Okay, so the goal of genetic algorithms, as I just talked about, so in genetic algorithms, we want to generate several possible solutions and test their fitness. And we keep those solutions that have a high fitness, and then those solutions that we keep, we change and mutate them in some way to generate offspring. And this offspring combined with the parents, we go back and we test their fitness, and we keep doing it, and we keep doing it until finally one of them gives us a nice solution that that minimizes the cost function beyond some threshold. Okay, so in genetic algorithms, we want to generate. I can't write today. Several possible solutions. Several possible, not solutions, but I would say combinations of parameters. And hopefully one of these will give us the solution we want. Hopefully one of these will give us the solution we want. Solution we want. Okay? So that's the whole purpose behind genetic algorithms. This is what we want to do. Okay? So we model genetic algorithms based on cell life and death. So you would encode these parameters into chromosomes, and each parameter inside a chromosome is a gene. And we mutate these genes in such a way that we will produce new parameters. We test their fitness, we check to see which ones we keep, and then we keep cycling and cycling until one of the chromosome, one of those configurations will give us the nice solution that we want. Okay? So each combination of parameters is encoded in a chromosome. Let me just get rid of this. Okay. Okay, so the set of parameters, so if you have, let's say, logistic or linear regression, theta 0, theta 1, theta 2, this set of parameters, one possible combination of these parameters will be encoded in a chromosome. And each little discrete unit inside this chromosome will be a gene, and one gene would occupy one parameter of that combination of parameters that you want. Okay, so each combination of parameters is encoded in a chromosome, and each gene is a parameter. It's a parameter itself. Okay, so what we do is in genetic algorithms, we stack all these parameters together into one chromosome, with each gene serving as one part of this chromosome. Okay, so each gene is a bit string. Okay, so zeros and ones. Okay, so for example, let's see here. Let me just write one more note. So for genetic algorithms, we stack our parameters. We stack our parameters inside a chromosome. And I'll give you a graphical example later, but I just want to make this point. And genes in a gene serving as one parameter. Okay, so each gene is basically a bit string. So what would happen is that you take each parameter and encode them into a bit string. So many parameters that we deal with are floating point, right? So you have, like, for example, a parameter might be 1.2, for example. So how you would encode this particular number would be using standard floating point representation. So there's 32-bit floating point representations and 64-bit floating point representations. You would take each of these parameters and represent them using the equivalent 32 or 64-bit floating point representation. It's known as the IEEE 754 standard. If you're not sure, but anyway, so each gene is a bit string. So most parameters are floating point, right? So how do you represent a floating point number in the sequence of zeros and ones? And that's actually what conventional computers use. You use floating point representation. So you can actually represent decimal numbers using 32 bits or 64 bits or whatever the precision may be. And this is what's known as the IEEE 754 standard. So use floating point representation. You can look up that standard if you wish. I'm not going to talk about that. It's beyond the scope of this course. But that's a 32-bit or 64-bit representation. And this is what is known as the IEEE 754 standard. I won't talk about that here, but this is how floating point numbers are represented in most computers. Okay? All right. So if we represent each parameter as a set of bit strings, right? So each parameter will be 32 bits, and then there's another parameter that's another 32 bits, so you have n plus 1 possible, times 32 bits. So if you were to change some of these bits, you would obviously generate new parameters. Okay? So what we want to do with genetic algorithms is we want to represent a set of parameters as a sequence of bit strings. And then you'd modify or mutate these bit strings in such a way that when you modify them, you create better solutions. So you keep mutating and mutating these, getting better and better solutions until finally you have a set of parameters that'll give you the best solution as possible. All right, so what you're doing is you're modeling, finding the parameters for your optimization algorithm or your training algorithm. You're finding the right set of parameters as a means of gene reproduction and life and death. Okay, so different patterns. Give you different parameters, which makes sense. Okay, so to generate new parameters, you modify the bit strings. Okay, so that's what you're supposed to do. So you modify the bit strings. So here's a nice graphical example of what I have. Okay, so let's see. Okay, good. Just want to make sure that I have enough time to cover everything. So here's examples. So in black, we'll have linear and logistic regression, and in purple, we'll have neural networks. Logistic regression, or SVMs, or whatever you wish. I cannot write today, so regression. Okay, and then in purple we have neural networks. Just some possible ones. Okay, so for example, we may have the following bit string. So what we do is we take all these parameters and we stack them into bit strings into a single chromosome. So this here, this is going to represent our chromosome. Okay, and we might have a sequence of bits, 0, 1, 1, right? And up to this point, this would be encoded as theta 0. And then the next one we might have, it might be 0, 0, and then up, 0 like this. From here is theta 1. And then you keep going up until the very end. You have 0, 0, and then 1 like this. And then this is theta n. Okay? So in this case, we may have 32 or 64 bits per parameter. And if there are n plus 1 parameters, you have n plus 1 times that many bits altogether. So you stack all these into one bit string. Or you may want to do this in neural networks. It's the same thing. So you would stack the weight of the first layer, from 0 to 1. And this might be 0 to 2 and so on. Sorry, 1, not 0. Okay, and you keep going, and then this might be the last one, right? Right, at layer L, something like that, okay? So that's one possible solution. And then you might have another one which changes, like, this here. Okay, and then this individually would be a gene, right? This is a gene, and so on and so forth. And you might have another one which is similar, but the bits may change, right? So in this case, you might have a 1 here instead of a 0, and you might have a 0 here instead of a 1. These may stay the same. This might change to a 1 instead. This may change to a 1 and so on. So different combinations of bit strings will give you different parameters. So you have A, B, and so on. Okay? So we have a population of all these chromosomes where each chromosome is different from another, which generates one possible solution that you have. And our goal is to take all these and mutate them and change them so that eventually one of these will give you the right solution for your cost function. Okay? So we have a population of parameters. And we use all of them. Or some, it depends, but all of them to find our optimal solution. Okay? So usually the population is kept constant. So if you have a cell culture, like let's say 200 cells, we usually try to keep the population constant. So if 50 were to pass away or die, you want to reproduce another 50 in order to maintain the population, in order to keep it constant. Okay? So usually the population is constant. Okay? So in order to compensate for this, when certain chromosomes die, you want to reproduce new ones that are better than the old ones in order to maintain that the population is constant. Okay? So when we generate new chromosomes, we discard bad ones and keep the quality of the solutions to be good by keeping the good ones. So if you keep continually keeping the good ones, when you decide to reproduce and generate new chromosomes, you have all these good ones that are used as a base blueprint. And then when you generate new ones, they're based off of a good blueprint, so hopefully you'll generate better ones than the ones that were based off on. Okay, so that's the whole point of that. All right, so we determine the right chromosomes to keep. Then we modify these so that better parameters will hopefully be generated. Better parameters are generated. Okay? So what you want to do in this case, if you want to figure out which ones you want to keep, you take each chromosome and put them through your fitness function, and then each of them is going to have a fitness score. You rank all of them and keep, let's say, the 5 best ones or the 7 best ones. So this is what's known as survival of the fittest. Only the best ones will survive. So let's say you've got 20 chromosomes, 7 of them you want to keep, and then you want to reproduce 13 more that are based off of these 7 to keep your population of 20 constant. Okay, so you discard some, you keep new ones, reproduce it until your population is back under control. All right? So you rank each combination of parameters and keep a few of the highest scored ones. Okay? And then you generate a new set of parameters based on these in order to keep your population constant. So a new set of parameters are formed from the best parameters that were kept. Set of that were kept. Okay? So that's what is usually done. Okay, so these kept parameters are, intuitively called the parents, and the new genes or the new chromosomes that you generate are called the offspring or the children. All right, so that's just another set of vocabulary. So the best set kept are called the parents, which makes sense. And the new set is called the children, or the offspring. The offspring or children, it just depends on what you read, but both of them are used quite often. Okay? So, when you create these new chromosomes, they're based off of 3 fundamental genetic operations. There is crossover, there's mutation, and there's copying or elitism. Okay? So, the generation of these new chromosomes are based off of 3 fundamental genetic operations, is what people like to call it. Okay. The first one is what's known as crossover. What crossover means is that, let's say you have 2 chromosomes, let's say A and B, and what you're doing is you're finding some sort of split point that is common between them both. So let's say chromosome A and B have 20 bits, and then you randomly choose position, let's say 13, and then what you're doing is you're generating 2 new chromosomes where you're taking the first half of part A and the second half of part B, you're making 1 new chromosome, and then the first half of part B and the second half of part A, you're making a new chromosome. So what you're doing is you're switching between the 2 chromosomes at that split point. You're crossing over between the 2 to generate 2 new chromosomes. Okay, so this is what is known as mixing 2 chromosomes together. Just see how much time I got. Okay, good. I got time. Mixing 2 chromosomes together. All I have to do is just cover these definitions, do the algorithm, and then that's it. Note that for genetic, I'm not expecting you to solve any problems. This is a very high-level concept because the algorithm itself requires randomized values. And you can't do that on a final exam. So I'm just doing this to, if I'm going to test you, I'll only test on conceptual or like higher level questions. Okay, so mixing 2 chromosomes together. So what you need to do is you have to define a split point. Is chosen with probability, we'll call P sub CO, probability of crossover, okay? So you're gonna choose some split point, and then the first part, so mixing 2 chromosomes, I'm gonna call this A and B, okay? So the first part of A is spliced with the second part of B. Okay? Also the other way around. I'll show you a graphical example soon. Okay? So what this does is that it generates 2 new chromosomes where each of them, you can think of this as if you ever read Mary Shelley's Frankenstein or actually watched the actual movie, you can think of splicing as taking the large body and splicing it with, someone's head, right? So you can think of that as crossover between 2 different species, I guess, but you're doing it in terms of the gene level. So this is also the other way around, okay? And then this forms 2 new chromosomes. Okay? So what this does is that it preserves and spreads the good bits from A and B and then reproduces 2 new ones that hopefully will be the same quality or if not better than the other 2. Okay, so this preserves and spreads the good bits from different parents, combining them to produce better solutions. Okay, so that's what crossover is defined as. The next fundamental operation is what is known as mutation. Okay, so what you're going to do is you're going to take some chromosome, and then what you're going to do is you're going to go through each of these bits and randomly flip them with some probability. So let's say for probability of 0.6, you flip each of these bits from 0 to 1 or from 1 to 0. So you're randomly inverting each of these bits to produce a new chromosome. Okay, so each bit in a chromosome changes or inverts with probability P underscore mu, so probability of mutation. Okay, so what I mean is that it goes from 0 to 1 or from 1 to 0. Okay, so what you're doing is you're taking chances to generate new genes from parent genes that will hopefully give you some better solutions. So this is more of a risk to take because when you just randomly start mutating bits, you may actually produce a worse solution. But there's some risk involved, and hopefully when you do this mutation, you might get a better solution, but sometimes you'll actually get a worse one. But we can toss those when we get to the ranking step. Okay, so takes chances to generate new genes from parents to improve quality. Quality and diversity, I suppose. Okay? And last but not least, we have the most simplest case, which is called well, not replication, but it's called replication. also called elitism. Elitism. Sometimes I can't speak. Simply what you're doing is you're not doing anything to the chromosome at all. You're just copying it over. And that's the most simplest case. So what you're saying here is that you think that this solution is so good enough that you don't have to change anything in the chromosome. You just copy it as it is. And usually this is a result of your algorithm converging, saying, hey, this is the best one we've got, so let's just forward it out. Okay? So sometimes called elitism, so just copy the chromosome. So you're not changing any of the bits at all. Okay? So used to keep the best solutions intact. Okay? So here's a graphical example of what I'm illustrating here. And then once I do this, I'll show you the genetic algorithm pseudocode, and we're going to finish up. Okay. So here's an example of all the operations I talked about. So this is the graphical example. Okay? Okay. So here, the top, we have the parent, and here we have the offspring. Okay? And then here is the operation. So the most simplest one is replication, which is also known as elitism. And this is basically taking the parent and copying to the offspring. So there are no changes done. Okay? So generation K, you can think of this as being iteration K. All right? And this is iteration K plus 1. All right? So we have two parents, A and B. So what we want to do is we want to define some, so this split point, this is a split point with probability, PCO. So we choose the split point at random, and then what we're doing is we're creating two new chromosomes where we take the first half of A and the second half of B, and we splice these together into one new chromosome. And similarly, we take the first half of B and the second half of A, we splice these together to create another chromosome. So you're Frankensteining them two together to create a new chromosome. So that's what's known as crossover. And mutation is pretty simple. All you're doing is you're going through every single bit, and with the probability of P MUT, you're just changing the bits from 1 to 0, from 0 to 1. Okay, that's like the most easiest one. So invert each bit with probability P mutation. Okay? And those are and then what I have next now is just, this is the final part. I'm just going to define the pseudocode, and then I will show you a graphical representation, and then we're done. Here's the genetic algorithm pseudocode. I'd like to point out again that I'm not going to test you on actually numerically computing this, is because this is a randomized algorithm. These are generating random values. It doesn't make any sense to test, but I will test you on general concepts to make sure that you understand. Okay? So given. We have several givens that we have, that we need to have. We have to define a fitness function, which is J. Okay? We also have several other parameters that we have to deal with. So this is the probability of crossover. Okay? This is the probability of mutation. So the little things there means that you're copying from the previous sentence. Okay? N, this is the length of a chromosome. Okay? Tau, this is what we call the fitness threshold. Okay? So what we're going to do is we're going to stop the algorithm when fitness exceeds tau. Okay, so if we find one particular chromosome that exceeds this fitness threshold, we stop. Okay? L will be the number of chromosomes to keep. And finally, K is the number of chromosomes at a particular iteration. So the number of chromosomes at an iteration. Okay, so here we go. The first thing you need to do is initialize. Okay, so when we initialize, what we're going to do is we're going to generate K n-bit chromosomes. So this is up to you. You can define as many as you can define. 20 initial ones, 40 initial ones is up to you. or you can cram as many as you can in memory. So generate K n-bit chromosomes, okay? And then the next one we're going to repeat until satisfied. And I'll talk about how to satisfy this in a little bit. So we're going to repeat the following to satisfy. So A, what we're going to do is we're going to determine the fitness of each chromosome. So determine the fitness of each chromosome. Okay, so this is F sub I, where I is equal to 1, 2, up to as many chromosomes that we have at the current iteration. Okay, and then what we're going to do next is we're going to rank the chromosomes. So what I mean by ranking the chromosomes is that you're going to sort them in descending order. So the highest ranked chromosomes will appear first, followed by the lowest ranked chromosomes, which appear last. Okay, so C, repeat until L offspring chromosomes are generated. So this is the survival of the fittest stage. Okay, so what you're going to do is you're going to select 2 chromosomes, A and B, with the highest scores. Okay, so once you figure out those 2 chromosomes, the next step that you're going to do is you're going to figure out whether or not you want to perform crossover, if you want to perform mutation. And that's what the probabilities define that operation. Okay, so generate a random value. We'll call this capital R, belonging to 0 but not including 1. Okay, now what we're going to do is we're going to check this value. So if R is less than the probability of crossover, this means that we should perform crossover with A and B. Okay, and we also want to keep the parents, because we want to keep those to be able to generate better solutions. Okay, else what we want to do, so that if we're not going to produce crossover, then what we're going to do is we're going to else perform mutation on A and B. Okay, so what you want to do is you want to mutate each bit of A and B with probability CO. Not probability, P mutation, not PCO, sorry. Okay, so in other words, what you want to do is for J is equal to 1, 2, all the way up to N, right? So they are, let's see, so there are N bits in total, okay? What you want to do is if AI is less than the mutation probability, set this bit to 1, else set this bit to 0. Okay, so what I mean by AI is the bit position I of chromosome A. So you can think of that as an array. And then you can do the same thing for B. Copy. Not necessarily, because, okay, think about it. If the probability of mutation was 0.9, I have a larger chance to generate a number between 0 to 0.9 than from 0.9 to 0.9 to 1. Oh, okay, so you know what, so let me just say invert the bit, not A is equal to 1. Okay, thank you. Okay. That's what I intended to write, but obviously I was writing these notes like the night before and they're pretty messed up. But yeah, I think you wanted to say invert the bit, right? Okay, invert the bit, thank you. Okay, all right, so you do that and then repeat, right? And then repeat, so 4 and then, yep, so repeat until satisfied and then we're done here. Okay, and then D. If any chromosomes fitness, I'm almost done. This is like my last slide. Exceeds, oh yeah, what I need to do here is, okay, so we perform comp to keep the parents, and then when you're done the mutation, you need to delete the parents. Just in case. So you keep the parents in the crossover stage, you delete the parents in the mutation stage. Exceeds tau, stop. And then finally, we have a chromosome whose parameters have a good fitness. And that's it. I've got one last slide. I'm just going to show you just a graphical diagram, and then we're good to go. Okay, so this is what this looks like here. So this is the genetic algorithm in a nutshell. Okay, so first we start off with, some chromosomes at iteration k. Okay, and this is time iteration k. So this is iteration. Okay, and then what we have is we have a bunch of scores. We have a bunch of scores. We rank them. We sort them. And then this here is that if the fitness exceeds the threshold tau, we stop, and then we want to keep L of these. In this case, this is 5. And then you generate new offspring until you match K again, and then you cycle back. And then you keep going until you find something that satisfies this condition. If you have some fitness that is greater than tau, you stop. Okay? So start off with K chromosomes, find the score, rank them, and then keep the best L of them, or you generate as many chromosomes until you have L. You have K again, and then you just keep going back until you're done. Okay? And that's genetic algorithms in a nutshell. So next week, we're going to cover 2 more algorithms, particle swarm optimization and ant colony optimization. That's part of the swarm intelligence framework. And then we'll do a final exam review. Thanks a lot.